Hello, good evening, everyone. So today we are going to start with week 12 open session. I hope you guys may have watched the lectures given by professors. So we'll discuss that. Okay. So till now, what we had done is, yes, anyone wants to speak? Yeah.
Ma'am, anybody who don't watch the lecture?
You can still continue the class because we are going to revise that lectures only. Okay, fine. Okay. So till now, what we had done,
Hypo- hypothesis testing.
yes, hypothesis testing. So, uh, like how the problem was created, uh, there are some situations. For example, there are from out of that situation, we create some samples, right? Where either we have given some information about samples distribution or some sampling is given to us. Out of that sample, what we do, we know about the sample distribution, right? And on the basis of that we create some hypothesis. And like there are two kind of hypothesis we assume. What are they? About the particular condition, right? Whatever we are going to choose.
Null and alternative.
Yeah, we assume there is a one null hypothesis and one is another one is alternative hypothesis. That means, let's say there is some xi are normally distributed IID like random variables, and they are normally distributed with some mean nu and variance sigma square. Okay, and actually not sigma square. Let's say they have given us variance as 25. Okay, and we are given that we are not sure about what the mean is. So but someone has claimed, or by somewhere we got the information that this mean is equal to 10. Okay, so we will be checking about whether the mean is 10 or is not equal to 10. So in that scenario we will have hypothesis, null hypothesis as mean is equal to 10, and alternative hypothesis as mean is not equal to 10, right? Or depending on the context, whether it's greater than 10 or less than 10, whatever it is, fine. So
Yes, ma'am.
we had samples that they are normal distributed, and their variance is known and mean is unknown, and we are going to estimate the value of mean, or we will check whether its mean is 10 or not. So we created two hypotheses. One is null hypothesis that says mean is 10, another says no, it's not equal to 10. Now uh, after that, what the procedure was, it says that have some test statistics on it so that we can test whether the mean is 10 or not equal to 10, right? To check whether the mean is 10 or not, we have to test something, right? So we have learned in last lecture a z test, right? Remember, we have discussed z test. What we used to do there, first, as we are going to check about the mean, so our test statistics will be what? Any idea? What do you mean by test statistics? Anyone? Like if this is what is your test statistics, but I will ask what is
Mm,
test
Ma'am,
statistics?
ma'am. Mean.
Sample me.
Sample mean. So in any kind of questions, whenever it comes about test statistics, it's nothing but something about the samples, like functions of samples. Here we are going to check about the mean. So obviously our function will be x bar, right? That means sample mean. We will check what is the sample mean, and on the basis of that only we will uh, like interpret something about the population mean. So in this particular case, our test statistics will be x bar. Is it a greater than some value C or not? That C, what C is here?
Critical
A
point.
critical value, right?
Critical.
A critical value that decides our acceptance and rejection part. Fine. So we had samples, then we formed hypothesis, null hypothesis, and alternative hypothesis. Then we found out what test statistic will be suitable for the particular question. So here it is mean. So I take test statistics as sample mean and just okay. Then x bar is greater than c. Then what will be the next part? So this x bar greater than c will lead us to a decision part, right? If the given sample mean is, let's say,
Is a right tail, left tail, or
okay. So how to decide that x bar is greater than c? That means this one is
left tailed?
okay. How do you decide left tailed or right tailed?
Right.
No, ma'am. So sorry, right tail.
Okay, ma'am.
Yeah,
Right tailed.
it's a right tailed.
No,
Okay.
but mu is not equal to 10.
Hmm.
The null hypothesis is mu is equal to 10, and the alternate hypothesis mu not equal to 10. So I think it will be a two-tailed test, right?
Okay. We will come to this. Just let me just finish the procedure. Then I will discuss how to check whether it's a right tailed or a left tailed. Okay. So after this, what we'll get using this critical value, we will decide whether to accept the null hypothesis or reject the null hypothesis. Now, I'm again giving a one value for sample mean. Let's say the sample mean is something 11 and your critical value comes to, like, we solve the problem and we come to know that the value of c is 12. Then what will you do? What will be your result from this conclusion, from this given scenario? That xi is our normal random variable whose sample mean is 11 and mean is 10 is our null hypothesis, and not equal to 10 is our alternative hypothesis. Then test statistics, we got to know that it's a x bar greater than c, and c is equal to 12 for, let's say, alpha is equal to 0.05. At significance level 0.05, we got c is equal to 12. Now, what will be your conclusion based on this? Obviously, we might have applied z test, right? Are you getting me?
Yes, ma'am.
Okay. So,
Z test is used for finding the mean, right, ma'am?
yes, finding the mean, or yeah, or any other thing also, but you can say that here we are finding mean only. For some alpha, we got c is equal to 12 and we know our x bar is equal to 11. Now what will be your conclusion? Is the mean of population is 10 or not equal to 10? What will you say? So here x bar is less than 12, right? See, your x bar is 11. What does test statistics says? X bar is greater than c is for what? If our x bar will come greater than c, then we will what? Reject or accept?
Accept.
Reject.
Reject what? Reject to what? H naught or HA? Like
H
null.
Not one.
H naught.
H naught.
Okay. So if this is the scene, then if x bar is 11 and c is 12 with this particular setup, then what will be our conclusion? We will say that
accept H no.
One
Accept.
question,
we
ma'am.
will, yeah,
Statistics test is a rejection criteria, no?
it's a not rejection. You can say yes, it's a rejection criteria.
If if some value of x bar greater than the critical value, then we can reject the hypothesis.
It depends. See, here I have taken my test statistics as, see, test statistics is x bar only.
Hmm.
Okay. And then I decided that if x bar is greater than c, then I will reject H naught.
Okay.
So this is what we decided our acceptance region and rejection region, right? Based on this X bar greater than C, right? Then we calculated C because for some alphas, for some fixed alpha, let's say, for some fixed alpha, we got C is equal to 12. So once you got to know that your C is equal to 12 and you know that sample mean is 11, that means 11 is less than 12, X bar is 11 and is less than C, that implies we will accept H naught. What does it mean by accepting H naught? We will say that for these samples, the mean might be equal to 10. Okay. Now let's let's have a discussion on one-tailed and two-tailed. So what do you mean by one-tailed and two-tailed? Yes, you can continue. Anyone like to answer? They can unmute and speak.
One tail या फिर right tail or left tail, no?
Yeah, one tail. See, one tail means either it has a it has a tail on right side or left side, right? Two-tailed means it will have tail on
Both
the
the
both
side.
sides. So now, given this setup, what do you say? Is it a right tail, left tail, or what?
Right tail.
So X bar greater than C. Let's say C is somewhere here. Okay, fine.
Close to this graph.
Close
The
to this.
right.
So X bar greater than C will lie where? On the left of C or on the right of C? So what is this shaded region shows?
Rejection area.
Rejection region. So from this graph, can you just tell me, is it a one-tail test or two-tail test?
One tail.
From the graph, it is right tailed.
Yeah. That means it's a one-tailed, and specifically if I say it's a right-tailed, right? Okay. Is it fine? What
Ma'am,
does it mean by two-tailed?
in one-tailed, both include right and left tail.
What?
Ma'am, in one-tailed test includes both right and left tail.
No.
Includes means
Like in which in one tail we can say that either right-tailed or
yes.
left-tailed.
This is X bar greater than C. Let's say I decided my test statistics is let's say test statistics is about X bar. I will reject H naught. Reject H naught if X bar is less than C. Okay. Then what will do? It will be a right-tailed or left-tailed?
Left.
Left.
Yeah, what?
Left tailed.
So let's say somewhere C here, yeah, and here X bar less than C. This is my rejection region. And it will be a left-tailed, right? So I can say it as a one-tailed test, which is specifically a left-tailed, right? Okay. Okay. What about this unshaded part? What does it indicate? The shaded part indicates rejection region. Then what?
Acceptance region.
Acceptance region. Yeah. Then you know one more thing, alpha comes into the picture. Like whenever you have a hypothesis testing, there is something what we call as alpha, a significance level. In this graphical part, where does it lie? Where is alpha and what does it mean?
Shaded region, man.
Shaded region is what? Alpha? Or area of shaded region is alpha?
Area of shaded region.
Right? Alpha is what? Probability of type 1 error. That is what? Type 1 error is what? Accepting
H
Accepting
not
H naught when
rejecting H not when H not is true.
true, right?
Huh.
So when H naught was true, that means null hypothesis was true, but we are rejecting it. So that is what alpha probability. So it's a area of this rejection region. Okay, fine. So I hope you guys are clear with this graphical representation.
Yes,
Any
ma'am.
doubt
Yes,
here?
ma'am.
Okay, any doubts?
No, man. No, no
Okay,
any doubt.
yes, what? Okay, so this was all about Z test that we have studied in the last week. Now we will study some more tests regarding these things, uh, but in a different manner. Okay,
Hello,
so
ma'am.
yeah,
Whether the letter JAD has some meaning or simply it's JAD test.
okay, let just a minute. See, there are something called Z distribution, T distribution, chi-square distribution, and all these things. On the basis of that, see, for example, let's say the same example I'm continuing. Okay. Uh, do you know we have some normal? Yeah, we says xi's are following normal distribution, right? Xi's are following normal distribution. Then when it comes to probability of that x1 is taking, just let's say x1 is some random variable which is following normal distribution, okay, with some mean and with some sigma square, and someone is asking what is the probability that x1 is greater than, let's say, mean 1 and sigma square is 4. X1 is greater than 2. Okay. Probability x1 greater than 2 is question mark to you. And if someone asks you how to calculate this, how will you answer them? You know some formula for normal distribution, right? Probability that xi is less or equal to, or let's say, x less than 2. That is also fine. Or less or equal to. Okay. So do you know how to calculate this kind of stuff? So we have probability distribution function for normally distributed random variable, right?
We will use the CLT here.
You can use CLT theorem, that is also fine. But yeah, that is also one thing. But in CLT, ultimately you are going to Z table. So I don't want to let you go there. Let's say instead of probability x less or equal to 2, I will ask this probability that x1 is ranging between 0 to 2. Then you will use that exponential formula. Do you remember? 1 upon square root 2 pi sigma square
Yes, ma'am.
exponential of what? Minus xi minus
Minus.
the whole square by twice sigma square, right?
Yes, ma'am.
So
Yes,
you
ma'am.
will put all these values here and find something, right? So this is what did you done there? You just calculated probability of x1 lying between this two value, right? Using how did you find that value, that exponential? Because we have did some studies and got to know that okay, whenever any particular random variable is following some particular distribution, then we can use whatever the studies has done over that, right? So similarly, there is something called Z distribution, or you can say the standard normal distribution. So in this kind of question, what we actually do whenever x bar is greater than c, and we are finding whether to accept the null hypothesis or not, what we do, we find what is our significance level, that is probability that what rejecting h naught when it was true, right?
Yes, ma'am.
So this is in mathematical term, if I write it, this is nothing but x bar greater than c, given that nu is equal to 10, right?
Yes,
In
ma'am.
particular, in our question. So what will you do next? Then probability, you will say x bar minus mean upon what? Sigma by square root n, right? That was sigma is some 5, right? upon 5 is greater than C minus 10 by 5, right? We will do this kind of stuffs there. And
Yes, ma'am.
we will find what is a value for this C. So here, how, like why we are able to write these things from this step to this step? Because we know that now this particular variable will follow normal distribution with mean 0 and variance 1, standard normal test, right?
Yes, ma'am.
And also known Z distribution. And using the Z table, that is normal table, we also it also known as normal table. Using this normal table, we will calculate this value, that is CDF of normally distributed random variable. Okay, and we will get our particular answer. So that Z represents that here, that your what we say, this random variable is going to follow standard normal distribution. Okay, is it fine?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So similarly, in all the tests, either it will be a T test, F test, or any test, the meaning is the final random variable, which will be a resultant uh, to us, that will follow some distribution, and uh, we have the CDF values of that particular distribution. We will use that, and so to just distinguish which kind of test or which table you are going to use, we just represent them by Z, T, or F, or anything. Okay, got it? So there is next test is T test. Okay, let me just tell me whether it's clear to you or not, so we can move ahead.
Clear, ma'am.
Yes, ma'am. Clear, ma'am. Clear.
So this is the basic test, and now we are going to move ahead. So T test. In T test, there is only one difference as compared to Z test. In Z test, uh, the variance was given to us.
Yes, ma'am. And here it is unknown.
Yeah. So let's say if there are x1, x2 till xn, some random variables that are, let's say, normally distributed only, and identically and independent distributions. And here they are following some mean and variance, but variance is unknown here. In that case, we will use t-test. Now, what is the difference there in between z-test and t-test? So as such, there is no, the main difference is variance is unknown. So just tell me, if I give you a sample, then would you be able to predict anything about variance? As like in the previous question, there was nothing given about the mean, but you were able to say something about the resultant mean using sample mean, right? Because we have studied that if xi's are independent and identically normally distributed random variables, then sample mean is nothing but the population mean, right? Is there anything about the variance?
So, ma'am, yes, ma'am, yes.
Okay.
Yes, ma'am.
Ma'am, we can say that the population standard deviation is equal to
Mm-hmm.
no. Sample standard deviation is equal to population standard deviation divided by under root of sample number of sample.
Okay.
Yes,
That's what you want to say?
yes, ma'am.
Fine. Very good. So let's say there are n random variables that are normal distributed and independent, also identically distributed. And we are also in this particular example also, we are looking for the mean only. Whether mean is, let's say, null hypothesis says that mean is equal to mu naught. Mu naught is some fixed number, okay? And
Okay.
alternative hypothesis says that it is greater than mu naught. Then what test statistics will you use in this particular case?
Sample mean.
Sample mean will be our test statistics. Okay, generally test statistics we represent it by capital T. Okay, capital T is X bar. That is our sample mean. Now, just answer me one question. Why are you using sample mean as your test statistics?
Because sample mean is given, right?
Is it given? Okay, let's say it's given or not. But still, why are you going to check that only? Why are you not going to check sample variance instead of sample mean?
We have a relation in between.
Because we want to conclude about the mean, population mean, right? If this question was about the variance, what is the variance? Let's say sigma is equal to sigma naught or not, or anything like that. We are making hypothesis for mean, sample mean. So, sorry, not sample mean, population mean, right? We are checking whether population mean is equal to mu naught or it is greater than mu naught. Okay. So, we will test about our sample mean and conclude about the population mean. Are you getting me?
Yes, ma'am.
Yes, ma'am.
In real life, if I say, uh, let's say in a particular state, let's say Maharashtra, you are going to check the average marks of 10th board, okay, in SSC exam in 2024. So, how will you do that? You are living in particular city and you have to check for the whole Maharashtra. So what will you do? Given that you do not have a lot of time to answer that question. So uh, we will take some sample. Like sample means what? The marks of randomly selected students, right? And
Yes, ma'am.
we will average it, and we will then, if that sample is good, then we will say that okay, average marks of this SSC board in scored by students in Maharashtra is this, right? So what have you done? What did you do there? You just collected a sample. You calculated sample mean and concluded about the total mean, right?
Yes, ma'am.
Yes, ma'am.
Okay. So we will go. We'll do the same thing. So sample mean and what will be test? Let's say test is, yeah. What should it be? Should I say X bar greater than C or less than C? Anything?
Ma'am, not equal to C, ma'am, because we don't know that.
Greater than C.
Ma'am,
Not equal to C, you can't calculate, you know.
ma'am, but why
Yes, ma'am. We can't
greater
calculate.
than C?
Yeah, what?
Why T greater than C? You take.
Yeah, that's what I'm asking. Like, it should be T greater than C or a T less than C or anything I can take here.
Oh,
So, in this kind of question, just observe what is your hypothesis there. Your hypothesis says mean is equal to mu naught or it is greater than mu naught. So, what should you take? Just think about it.
Greater.
T is greater than C, ma'am.
yes.
Okay. Then reason you should provide it.
Because you are considering mu is greater than mu naught. The same, what your what is the alternative? You have to take that as the test.
Yeah, because it may be possible that C and nu naught, let's say C is equal to 10 and nu naught is, let's say, 10.5, right? And if we are taking T less than C, then it will contradict again. Both the hypothesis and test will contradict, right? That's why this is mandatory. Okay. But in the above question, I took both the cases, right? Greater than C or less than C. Why it was possible? Because just observe what was my alternative hypothesis, right? Okay.
Yes, ma'am.
Yes, ma'am.
So, okay. So,
Ma'am,
One
yeah.
thing,
ma'am,
uh,
in the two-sided test, if we had said that T is not equal to C, then
Mhm.
it means whenever we are accepting that time T equal to C, right?
See, T equal to C means in that whenever you take T as equal to C, that is actually you are not taking the region, you are taking the particular value for your samples. See, what is T? T is sample mean here.
Right,
You are saying T not equal to C or T equal to C, let's say,
right.
right? Let's say you are saying T not equal to C, okay?
Yes,
That means whenever your sample mean is not equal to C, you are going to reject your null
reject.
hypothesis, right?
Right, right. Reject.
So what does it mean?
It means
Let's say there is sample one, okay? Sampling one, that means you have values for n random variable and you calculated its sample mean, let's say x bar 1, okay?
yes,
And let's say this is not equal to C, then you will say that reject null, right? You are going to rejecting null,
yes,
okay? But just think about it. Will it be a valid or a good test to check? Because the same example, just take the same example that Maharashtra students SSC board result, okay? You are, let's say, some 40 students and all will take randomly different samples, right? Okay. And let's say, obviously the sample mean by all of you 40 students will be different sample, will give me a different sample mean, right? Is it fine?
yes,
I have asked some 40 students of this course that just tell me what is the average marks scored in 10 student by Maharashtra in Maharashtra state. Okay, so 40 students are doing the task, so there will be a 40 samplings, right?
yes,
And this 40 samplings will give me a x1 bar, x2 bar. Let's say this is their roll number, okay, who are performing the test. So there will be a 40 sampling means, okay, and we are deciding, okay, whenever the sample mean is going to be equal to C, then only we will accept H naught. Otherwise, we will say that mean is something greater than mu naught. Is it fine?
okay,
So if there are 40 sample means, it may or may not be possible that out of this 40, only 1 or 0 xi will give me the T is equal to C, right?
yes,
So what I did, like instead of having selection, having acceptance region, I just give acceptance value only, right?
okay,
See, whenever we say T greater than C or T less than C, let's say T greater than C. So this is my rejection region. Whenever the values of X bar will follow in this region, I will reject my null hypothesis, right?
yes, yes,
But if we say T not equal to C, so let's say T is somewhere here, this line is T, okay? Let's say this value is C. T not equal to C, what will be my rejection region then? Right?
yes, right.
Because T not equal to C,
Equal to C.
I am going to reject the hypothesis, null hypothesis. So
Yes,
this all the shaded region is what?
the rejection reason.
Rejection region. And when there are uncountable samplings are possible, obviously it is uncountable, right?
Yes,
Because in Maharashtra, let's say 10 lakh or 20 lakh peoples will be going to, or more than that. Or if this was even a small example. If I say the whole India, then the it will be more complicated and lots of possibilities are there, right, for sampling. So when there are such a large number of samplings are possible, and I am saying my rejection region is this much, that means there are 100% chance that the given null hypothesis is going to be rejected always, right?
Yes.
Are you getting me?
Yes, got it.
That's why we do not take a particular value as our test statistics. Okay. Generally, we'll see that it's greater than C, less than C, and kind of this. Whenever it is, see, this equality kind of things will come when we study this two sample test. Okay. This was a good question actually. I hope you guys understood why we do not take a single point as equal to or not equal. Okay.
Yes, got it.
So, okay. So now we have a setup where we have some random variables that are normally distributed with unknown mean, unknown variance, both. And we just set up all these things. Then what we'll do? So, yeah, alpha will be what? Probability of rejecting H naught given that it was true. So if we write the same thing in terms of t or x bar, t greater than c, given that it is true, that means mean is equal to mean mu naught. So what we'll do? Probability that x bar minus mean upon, instead of variance, we will take a sample variance, right? Greater than c minus mean naught s by square root on. Is it fine for everyone?
Yes, ma'am.
Yes, ma'am.
So here, whenever we have this kind of stuff, t minus mean upon s by square root n, this is a random variable, okay? Because it is again a function of random variable, so this particular formation is also a random variable, will follow a distribution known as t distribution, okay? Will follow t distribution. And in t distribution, we say that if there are n random variable, it will have n minus 1 like degree of freedom. Okay, so whenever there is a thing that t minus mean upon s by square root n, it will follow a t distribution with n minus 1 degree of freedom.
Ma'am,
Whenever, yes.
what does degree of freedom mean?
Degree of freedom will depends on things, but as of now, you can say that there will be a n random variables, right?
Yes.
So, like how much independence you can have in your particular data set, that's what something degree of freedom. So I will just explain these things when we will discuss that chi-square and all, because there it will be like we will get a more clear idea about it. Okay.
Okay.
Okay. So in Z test, what we used to have that there was t minus mean upon something sigma used to follow what? A normal distribution with mean 0 and variance 1, right? A Z distribution. So here again, see, now this particular part is going to follow a t distribution, right? With n minus 1 degree of freedom. So we'll say this part will be equal to what? Anyone can? T n minus 1 is greater than, let's say. So again, if it is following some distribution, okay, let's say this kind of things, c minus mean naught upon s by square root n. If there is a distribution, then obviously there will be a PDF and CDF, right? And we are going to we are checking what is the probability that this distribution is taking values greater than this one. So Can we write it as 1 minus probability Tn minus 1 less than C minus mu naught upon S by square root n? Do you agree? Can we write it like this? Just it's
Yes,
just a different notation instead of x, y, and z. Okay, we have done this kind of things earlier also. Let's say x is following normal distribution, then what is the probability that x is greater than 3? What we used to do? We used to do 1 minus probability x less than 3, right? And it's CDF, the same thing. So its CDF is we can check in the T table, and the thing we just write it like Tn minus 1 of C minus naught upon S by square root n. Okay.
What is
So
S here?
S is sample variance. Sample variance.
Ma'am, sorry, ma'am. The T distribution, I'm not able to understand, ma'am. It's the same as normal, right?
It's not same as normal. Whenever there is some random variable, will be operated like this, like subtracted with the mean and divided by a sample variance upon sample variance as a whole. Okay, S by square root n is sample variance ultimately. S by square root n. Then we'll say that, yeah.
Ma'am, how become S divided by root n become?
Sorry.
Ma'am, how you can say that S divided by root n is a sigma?
Okay. Whenever let's say xi's are independent random variable, right?
Yes, ma'am.
They are IID, normally distributed random variable, let's say. Okay, not standard, anything. Okay. Mean and sigma square. Then if I ask what is the sample variance, then what we say?
Sample variance is equal to the ma'am sample variance
Sigma square by n.
population variance by n, ma'am.
Population variance by n, right?
Yes, ma'am.
So whenever sigma is unknown, we just try to make it like because sigma is not known, instead of that sigma we will put there a sample variance. Okay, just to like that is the actual difference between a Z test and a T test. Okay, they are not similar. In Z test we have known sigma, so we just directly put there. Here we do not know what is our standard deviation, so we just write it S by square root n.
Okay. It means that we directly put the sample variance in at the place of population variance.
Yeah, and why we have to do that? Because ideally it should be sigma by square root n, right? But sigma is not available. So once it changed to sample variance, the distribution, which if I write sigma here, then obviously this thing will be not a new distribution, right? This will be a normal distribution with mean 0 and sigma 1, right?
Yes.
If I write, instead of S, if I write sigma by square root n, okay, then what is the difference between this part and this part? Then instead of, if I know the sigma, then instead of this, then there is no matter to write this division by sigma square root n, right?
Yes, ma'am.
Then obviously it will be a normally distributed thing. So this particular arrangement makes it a new distribution known as T distribution whenever variance is unknown, and we are going to check what should be the mean of the particular distribution, then we will use T distribution. Okay.
It is simply means that whenever we don't know the population variance, we simply put the sample variance instead of population variance. That distribution called as T distribution.
Yeah.
Okay.
Okay. So here, just coming back to this. Okay, so the major difference between, yeah, if xi's are normally distributed, sorry, they are identical also. Xi's are IID and normally distributed with some mean and with some variance. There will be two cases. If sigma square is known, then just say, and we are going to check about, let's say, mean. Okay. Mean. Okay. We are going to make the estimation for new prediction or prediction. Yeah. We have some n random variables. Okay. N. Okay. I is equal to 1 to n. So there are n IID samples which are normally distributed, and we are going to check about its mean, what will be its population mean. And the condition is sigma square is known to us, then we will go for the Z test, okay? And if sigma square is unknown, in that case, what we'll do? We'll go for the T test. Fine. The difference between why it is Z test and why it is T test, the difference is this one. Because whenever we go for the Z test, we know the sigma, so we will make our X bar to follow a normal distribution with mean 0 and variance 1. So that is also known as Z distribution. So we say it as a Z test. But in the second case, when variance is unknown, population variance is unknown, so we'll replace it by a sample variance and divide it by square root n. That random variable will going to follow a T distribution. So we say it as a T test. Okay, that is the only difference. Now coming back to that degree of freedom things. So whenever there is a T distribution or any like chi-square distribution, F distribution, there will be one more term that is known as degree of freedom. So how many random variables are there? If n random variable or n variables, okay, these are random variables, but on the particular test, whenever you will have, so they are ultimately of variables, right? This term degree of freedom you may have heard in your physics also. Do you know what do you understand by degree of freedom? That is the only sense here. So just tell me, what do you understand by just degree of freedom?
Number of independent distribution.
Yeah, number of
Independent distribution.
Number of independent distributions, not independent distributions. See, these are random variable, and when you do particular operations, they are just variables for you. So whenever there are, let's say, n random variables or n variables, out of that variables, the number of independent variables that can be estimated. For example, there are many tools. See, this xi is following normal distribution, right? That is given to us. Okay, that's why we are able to do things ahead, right? That hypothesis, we are taking mean equal to mean naught and all this stuff. So in short, I just want to say, if there are it's a degree of freedom is number of independent variables that can be estimated using some statistical procedures. Okay, so now this may confuse you, but we in actual reality problem, this xi will follow normal distribution. This research is also important to us, and for that we just say, okay, there are n random variables. Out of this independent variables, how many number of variables are there that can be estimated using statistical analysis. Are you getting me?
Ma'am, Xi is IID, no, ma'am. So there are n independent variables, right?
Yeah, but that we got to know already, right? This is given to us already. But
Yes.
when there is no setup,
Okay.
at that time, we have to check, given this scenario, how many independent variables are there that can be estimated. Okay, estimation is there in like particular analysis. So I will not suggest to go in that details as of now. As of now, you just say that it's like it's something about the independence of variable, even though then that's why it makes it more confusing, because xi's are independent in identically and independent distributions, right? Independent and identically distributed random variables.
One
Then
more.
you are saying why it is taking, when it's come to t-test, why you are saying that it has n-1 degree of freedom,
Yes,
even
ma'am.
though all are independent. So that both the things are totally in, like they are not related to each other when it comes to a degree of freedom. So that is something else that's not in your particular course, but just understand that there is one thing you know, that actually I think, yes, we have studied that. Okay, that will help. Do you know that when we were calculating sample variance, estimation of it using MLE, maximum likelihood function, sample variance. What was sample variance actually? Unbiased, biased. Do you remember? The sample variance which is not biased is actually sigma square, sorry, is what? S square by n-1. Do you remember something like that? Whenever the sample variance is at sigma square upon n, like instead of this, you just write this one,
Yes,
1
yes,
upon
ma'am. In case of sample,
summation I is equal to 1 to n, it is xi minus x bar the whole square, right? In that, when we used to calculate sample variance, we used to do this n-1. This was unbiased.
Yes,
This
ma'am.
is the only thing where this t distribution has n-1 independent degree of freedoms. This is somewhat there. It's somewhat linked there. Okay. So it is actually the number of independent variables that can be estimated. So yeah, this only. So there are when there are n random what we say random variables, and we are going to apply t-test on that, then there are actually n-1 random variable which are actually can be estimated independently. So just will make it more complicated. So I will just say for timing, just make use of it to just calculate how to calculate the values of t table and how to find that. In further courses like statistical computing and all in your next semester, it seems you will get to know that how this from where this comes. Okay, does it convince, like is
Okay, ma'am.
it is
Yeah, we just
something
have to
related to
remember.
that what we say biasedness, unbiasedness that we have studied in maximum likelihoods things, right? When we were doing estimation before some 2 weeks or 3 weeks ago, we were doing estimations, right? That estimations, some estimations were biased and some was unbiased estimator. Do you remember that?
Yes, yes, ma'am.
Yeah. So whenever you get biased estimator, that is not the actual independence, like degree, that will not give you the degree of freedom. But whenever you get unbiased estimator for any particular operator, for any particular parameter, then only from that thing only you will get to know that how many degree of freedom the particular sampling has. Okay. So if you connect, like if you revisit that estimation chapter again after listening to this, you will get to know that from where this degree of freedom is coming from. Okay, I gave you one example of that sample variance. Similarly, there are a lot of. Okay, so that is the only explanation for it. It's estimation kind of things. Okay, so coming back to this t-test and all. So rest of the part will be same as we did in the z-test. After that, there is chi-square test. So is there any doubt regarding t-test and z-test?
No, ma'am.
Okay. So let's say there are n random variables which are normally distributed again with mean mu and sigma square as a variance, and let's say they are IID also. And it is given that now I tell you the difference between t-test and z-test. So just remember this test, where to use which test. So in this particular scenario, we were checking for mean, right? Our hypothesis was centered for population mean. Now, if the same scenario is for variance, like what is the variance? Let's say our null hypothesis is about variance is equal to sigma naught, and alternative hypothesis is for sigma is, let's say, greater than sigma naught. Okay. In that case, we will not use z-test or t-test. Why? We used to check whether sigma square is known to us or unknown to us, right? In this particular case, mean and variance is there, and sigma, we are checking for the sigma square only, whether the claim for sigma square is true or false. In that case, we need some new test known as chi-square test. How to use that? So now, as we are going to predict or conclude about the population variance. So, and we have the information about sample. So what will be our first task? Just calculate our sample variance. So whenever you want to predict or conclude about your population variance, in that case, you will always use your unbiased variance. Okay, unbiased sample variance. That is what? 1 upon n minus 1 summation I that we just discussed, right? Xi minus x bar the whole square. Okay. Because why we are using, why we are not using here n on n? Because we have to conclude about the population variance. And when you have to conclude about something, then just try to use its unbiased estimator instead of biased one. Okay. So what should be our test here? Can you guess? We have to check about the variance, or let's say standard deviation. Okay. And you have something about sample variance. S should be greater than C. Will it work? Are you getting what I am doing here?
Sorry, ma'am. Can you repeat once? I lost my connection.
Okay. Anyone else? So the setup is we have n independent and identical distributed random variables which are normally distributed, and we are going to check whether the claim about population variance is correct or not. That means whether your standard deviation is equal to sigma naught or it is greater than sigma naught. So we have this null hypothesis and alternative hypothesis. So we will create our test statistics which says that S square is 1 upon n minus 1 summation xi minus x bar. I will use unbiased estimator of this variance. So now what will be my test? That is S greater than C. Is it fine? Any doubt here why we have not take mean?
Why
Okay.
C? Which is why C, ma'am? Any constant?
C is critical value.
Okay.
Critical value. Yeah.
Here also mu and sigma are unknown.
Mu and sigma. Sigma is unknown. Mean may be known. Yeah, let's say mean is known. Okay. So if this is the scenario, then how to do the things then? And yeah, one more thing I should say. The ratio of variance follows the chi-square distribution. This is the things like whenever there are two distribution, let's say x is following some distribution, no, x is normally distributed, okay? Chi-square is also, once again, it's a kind of distribution like you have studied Bernoulli distribution, binomial distribution, exponential, like that only. This is also one of the distribution, okay? Now the question is, which variable will follow this kind of distributions, okay? If there are two random variable, x1 and x2, and they are, just a minute, okay? Let's say x1 is following normal distribution. It's not visible, right? Yeah, this is normal distribution with its result. With mean and some variance sigma 1 square, let's say. And x2 is also following a normal distribution with mean nu and let's say variance as sigma 2 square. In that case, do you remember this mean and sigma, whenever you will take a sigma 1 square, a ratio of two variance, okay? Let's say they are also a kind of, whenever we have the ratio of variance of two normally distributed random variables, they will follow a chi distribution with certain number of what we say, degree of freedom n minus 1. Okay, so here if xi's are normally distributed, okay, they have variance sigma square, okay, and s square is what? If your x1, x2, xn are normally distributed, then what about your sample variance? Will it be a normally distributed? If you look here, this is also a function of random variables, isn't it?
Yes, ma'am.
It is also what we say, normally distributed. So we will say, so if I say s square upon sigma square by n minus 1 will follow a chi distribution. Is it fine for you?
Yes, ma'am.
Okay. Why? Because this is also a variance, this is also a variance, okay? And both are different. This is the variance for xi's, this is the variance for particular sample, right? Sample variance. Okay. So this is how we have our chi distribution. When will it come into picture? Whenever there are things about to check for variance, we will take the ratio of variance, and this ratio of variance will follow a chi distribution. Okay. So now our test statistics is S greater than C. for particular significance level, alpha is what? Significance level, right? In all the tests, we check at which significance level you are rejecting or selecting, rejecting or accepting null hypothesis. So how to check alpha? Alpha is what? Probability of rejecting H naught when it was true, right? So how to write here that thing? Rejecting H naught means S greater than C. Fine. Yeah. This is equal to probability of that S is greater than C, given that variance is what? Sigma naught, right? This is our null hypothesis. So I will say, given that H naught is true, that means sigma is equal to sigma naught. So can I say this as probability that S square is greater than C square, given that sigma is equal to sigma naught? Is it fine? So once I do that, because I just squared both the sides, that's it. Now, the similar thing as we used to do, if mean is equal to mean naught, we used to introduce this into inside. So what I will do here, as we know that S square by sigma square will follow a chi distribution. What I will do is I will just divide both the side by sigma naught square, okay, and multiply both the sides with n minus 1. Okay, n minus 1. Is it fine? Now I know that this particular part is going to follow a chi distribution, right? Chi-square distribution. Are you getting me? What are we doing here?
Yes, ma'am.
The same thing, but just a simple variations there, okay? Greater than C square n minus 1 upon sigma naught square. So, as if this is a distribution, then obviously it has a PDF and CDF and all this stuff, and we will have 1 minus f chi square of n minus 1 C square n minus 1 by sigma naught square. Okay, that will be our significance level. Using this, if significance level is pre-decided, then using all this stuff, we can find the value of C. Okay. Once you got the value of C is equal to C naught, then obviously from the sample you can check your sample mean and check whether that sample mean S is greater than C. If it is greater than C, you will reject your null hypothesis. Otherwise, you will accept your null hypothesis, right? That's how we decided our test statistics. Do you get it? See, in all the tests, we are going to do the same things. We have samples which will follow some distributions. Okay, step 1. Step 2 is decide a null hypothesis and alternative hypothesis. We just said that okay, it is equal to sigma naught, and alternative is sigma is greater than sigma naught. Then decide our test that if S is greater than C, then reject H naught. Okay, that is our what we say test statistics. Okay, so how to check whether S is at which point S will be greater than C or not? So after that, I just introduced one more thing, that is what? The ratio of variance will follow a chi distribution, right? So if and you know that significance level is also known to us that either it will be a 0.05 or 0.0 or whatever the value given to you. Then how to calculate alpha? Alpha is nothing but the probability of type 1 error. We just applied the mathematical terms here and we got to know that okay, this is again going to follow a chi distribution, and once you reach to chi distribution, you know how to calculate these values because we have tables for it. There will be a chi-square table, Z table, T table, chi-square table. Whenever f chi-square you are going to search for that, you have to search it in the chi-square table. Okay, and we will using all these values, either C is given to you or alpha is given to you, and we will be able to find out what is the value of C. If C is equal to C naught and let's say S is greater than C naught, then what will you do? S is greater than C naught, then what will you do?
Reject the H.
Reject H naught, right? Okay, so that was about chi-square distribution. Any doubt here?
No, ma'am, it's okay.
It's okay, fine. So, do you guys got to know that when to use chi-square test?
When we have to find the variance.
Yes, then we have to find the variance. Then only we will use chi-square distribution. Okay, so till now we covered 3 tests, z-test, t-test and chi-square test, right? So when to use z-test? When we are checking for the mean and variance is known, go for the z-test. If variance is unknown, go for the t-test, right? Variance unknown. And then if we are checking for the, or we have to conclude about the sigma, in that case, we will go for the chi-square test, okay? Now, in all the above tests, we have only one sample. That one sample means only xi's were there, only one parameter was there. Now, we will have two things. Let's say xi's are following normal distribution, are normally distributed with mean and some variance, and all are independent and identically distributed. Similarly, there are another parameter, another random variables yi, and they are also independent and identically distributed, and they have some mean, let's say, okay, let's say 1 and 2, sorry, 1. Nu1 square, sigma 1 square, and here nu2 square, sigma 2 square. Okay, so there are n2 IID samples for xi's, and for yi's they are, sorry, n2 and here n1. Okay. So n1 xi, like x1, x2, x3 till xn1 random variables are there, which are normally distributed till with mean mu1 and sigma 1 square. Okay. Similarly, yi's are also identically and independent distributed random variables, which has this normal distribution. Okay. It may be possible that in some scenarios, your xi will follow some, let's say, exponential distribution, and yi are following normal distribution. But in this particular part, we will be looking for normal distribution only. Okay. And one more thing, this xi's and yi's, they are also, in between them also, they are independent. Okay. Now, if this is the scenario, then what about x bar and y bar? X bar will be a sample mean, right? X bar is a simple mean, and it is nothing but the function of random variables, right? Do you agree? This is nothing but x1 plus x2 plus till xn upon n. So this is also a random variable, right? If x bar is a random variable, then what will be its distribution?
Normal mu sigma square by n.
Yes.
mu1, sorry.
1, and variance will be sigma square by n1. And similarly for the y bar, they will be normal distributed with mean nu2 and variance as sigma square by n2. Now question will arise, what are we going to check? Oh, sorry, sigma 1 square and this is sigma 2 square. Okay. X bar, y bar are known to us. So similarly, okay. So then there will be one more thing. Let's say we are going to check instead of checking, let's just check what will be s x bar square. If I say, what do you mean by s x bar square? Will be a variance for this sample mean, right? Isn't it?
Yes, ma'am. Yes, ma'am.
Okay. if I say this is divided by sigma 1 square by n minus 1, then what will it follow? This is also a kind of distribution, right?
Chi-square.
Yeah, it will be a chi-square distribution with n1 minus 1. And similarly for y also, n2 minus 1. Upon sigma 2 square will be again a chi-square distribution. Okay. So now, if x bar is normal distributed, y bar is normal distributed, there is one more thing, x bar minus y bar. What about this? What will be its distribution? If xi's are normal distributed, yi's are normal distributed, then their linear combination is normally distributed. What about x bar and y bar? Now again, this is a random variable, this is another random variable. What about their difference? Will they be normal distributed or not?
Yes, ma'am. Normal distribution.
Because it's ultimately a linear combination, right? Then just tell me what is its mean and what's its variance.
Mu1 minus mu2.
Mu1 minus mu2.
Mu1 minus mu2.
Then class of
Sigma
variances.
and addition of variances.
Why addition?
Because minus becomes plus minus 1 whole square.
Yes, because when it comes to variance of x bar minus y bar will be equal to variance of x bar plus minus 1 the whole square, because it's a constant there, and variance of y bar. Okay, so that's why it is addition. Okay. So now this was all about that. Now what if I say s x square upon sy square, both are sample variance, right? In that case, there is one more distribution that is known as F distribution, with number of like obviously n1 minus, like how many distribution it has, n1 minus 1 and n2 minus 1. Actually, this is nothing but the okay, let me just explain it. So now there is one more new distribution is introduced to you, that is F distribution. As I said, just a minute. As we discussed here, chi-square distribution. Similarly, there is one more distribution, F distribution. It says that whenever there are whenever let's say there is chi distribution, two chi-square distributions are there. Let's say chi with degree of freedom, let's say n1. When we take the ratio of two chi-square distribution, it will give us along with its degree of freedom, it's n1 and n2 only. Then the ratio of this chi distribution will follow F distribution with degree of freedom n1 and n2. Okay. So this is one of the again new distribution introduced to you. For this, if it is a distribution, then obviously it has a PDF and CDF and all this stuff. F distribution, you will always see its diagram like this. It will be something like that. It's not symmetrical like normal distribution, but this is also one of the distribution that you will come across when whenever you will do real life questions. you will see this kind of distributions also. Okay. So chi-square distribution was actually the ratio of two variances. When we take, they follow chi-square distribution. The ratio of two chi-square distribution divided by their degree of freedom will follow a F distribution. Okay. Is it fine? So now onwards, whenever we will have two sample test, there will be a term or there will be a new distribution will be introduced to you, that will be a chi distribution. In this particular case, I have taken one assumption that I should write here, that let's say sigma 1 square is equal to sigma 2 square. So this is nothing but actually this one. Okay. If they are equal, then obviously they will get cancelled, right? Otherwise, you should ask me that question, that Sx square and Sy square are sample variance and you are taking the ratio of that, so it should follow chi distribution. Why are you saying that it's following F distribution? Isn't it a valid question?
Yes, ma'am.
So there was a thing that if in a case when variance of xi's and variance of yi's are same, then if we take the ratio of that, then it will follow F distribution. Now, do you agree it will follow F distribution? Because this is not a ratio of two variances, it is the ratio of two chi-square distribution, as we discussed here only, that they will follow a chi distribution. Okay. Okay, is it fine? Whenever it is, yeah. So these constants can be adjusted, but just take care of these things. Okay, so if they are equal, then obviously they will get cancelled and you will get Sx square and like S square x and Sy square, sorry, Sy bar square. They will follow F distribution. So let's have a proper setup now. So now you know what is F distribution. So I am introducing a two sample Z test to you. Okay. The important part is in hypothesis testing, just be clear when to use which test. Okay. Like that's why I'm every time I'm discussing this thing, that if we are discussing about mean, then there are two options, either Z test or T test, depending on if the variance is known to you or unknown to you. If you are checking for the variance, then don't go for the Z test and go for the chi-square test. Now, if there are two samples, like xi's and yi's are some random variables, x1 to xn1, let's say, following normal distribution, they are IID also. Normal distributions with mean nu1 and sigma 1 squares, and similarly y1 to yn2 are some IID samples which are normally distributed and whose mean is nu2 and variance is sigma 2 square. Okay. In that case, if it is given that we have to check whether the mean of xi's and mean of yi's are same or not. That means this nu1 and nu2, are they same or not? So our null hypothesis is nu1 is equal to nu2, and obviously alternative hypothesis is what? Mean is not equal to nu2. Then if we are dealing with the mean of actually two samples, right? Two different kind of samplings are there, xi's and yi's. Then what should be our test statistic T? Remember, when we have only one sample, we used to do the sample mean, right? If this yi things are not there and only xi, we are checking whether the nu1 is equal to some value or not. In that case, our test statistic was only x bar, right? we were used to check over whether the x bar is greater than c or not, right? But what if we are going to check whether the mean of xi's and mean of yi's are same or not? So for that, what we'll do, I will just take x bar minus y bar or y bar minus x bar, whatever you say, modulus t. Okay. I will just find x bar minus y bar. If this value is equal to 0, then what will I say? They are equal. But I will not take again a value equal to c. Why? Value equal to 0. Why? As I discussed there, if I take modulus t as equal to 0, then instead of taking region, I am taking only a point, right? That is not a valid testing because we do not know much more things about that. So we will have some, we should have some limitation, right? Delta value, because in that delta value, if variance is the difference between the two mean is lying between some particular is difference is till particular point, then it's acceptable, otherwise reject it. Okay, so this is what, then reject h naught. Okay, are you getting it? Yeah, any doubt here?
No.
Okay, so modulus t greater than c. Now what to do? As usual, we will go for the alpha. Do we know anything about x bar minus y bar? So I have computed that, right? That time you might be thinking why she is doing all this stuff. So yeah, we know that x bar minus y bar is going to follow this normal distribution, right? A normal distribution with mu1 minus mean, this one, and variance as sigma 1 square by n1 square plus sigma 2 square by n2 square. Okay. So can I say that t is following normal distribution x bar minus y bar, right? Minus mu2 and sigma t square is what? Now, what is my significance level? Significance level is again what? Probability of rejecting h naught when it was true. H naught is true in this particular case implies what? Implies here what? H naught was actually mu1 is equal to mu2, right? So if I say h naught is true, that implies what? Difference between mu1 minus mu2 is equal to 0, right? That means the nu t, if I say, that has to be 0, right? This t is following normal distribution with mean mu1 minus mu2. If we say h naught is true, that means they have to be equal. If they are equal, then this is a normal distribution with mean 0 and variance sigma t, let's say. Okay, so we will make use of it. So alpha is actually probability that modulus t is greater than c, right? That is our test statistics here. Given that mean 1 is equal to mean 2, right? So what does it mean then? If mean has to be, both the means has to be equal, in that case, if I, let's say, then if mean, sorry, if our mean 1 and mean 2 are equal, that implies t will follow what? 0, and let's say difference will be a 0 and sigma t square, let's say. Is it fine if I say sigma t square is nothing but Okay. So to this t, if I divide by sigma t square, then what will happen? What will be my new variance then? If alpha is this part, then if I divide this t is a random variable which is following normal distribution with mean 0 and variance sigma t square. If I divide it by sigma t square again, instead of sigma t square, I will just divide it by sigma t. Then what will be the distribution for it? Yeah. If I have t by sigma t, then what will be the distribution for it? Will it be a normal distribution with mean 0 and variance
1.
1? So what is it? This is nothing. Again, if we have anything following normal distribution with mean 0, variance 1, we can use that test, right? So that's why from this only, from this alpha value, if I use that type 1 error, if I calculate it, I will get it to know this is nothing but probability modulus t greater than sigma t is greater than c by sigma t, right? As I applied mean, both the means are equal, so I will get to know this, right? Is it fine? They are equal. Now, this part is going to follow a normal distribution, 0 mean. So can I write it as nothing but the 1 minus z test fz of c by sigma t? Is it fine?
Yes, ma'am.
So that's it. As it is a so we started from two sample test, like there were two samples, right? Xi's and yi's. They are independent, identically distributed and normal distributed. And we were looking for whether the mean of xi's and yi's are same or not. So what we did, we just took a test statistic as the difference of sample means of xi's and yi's, right? And then we choose the test as we used to, that this modulus value, the difference between x bar and y bar, should be a greater. If it is greater than c, then we will reject h naught. Otherwise, we will accept h naught, right? So we got to know that this t is distributing, t is following some normal distribution with some non-zero mean and some variance. Then once, if we are going to check what is type 1 error, then according to that, it is nothing but the probability of rejecting h naught when h naught is true. Now, if null hypothesis is true, means both the means are equal. Once both the means are equal, then t will have mean as equal to 0. If t has mean 0, then we have one liberty that we can make it to a standard distribution by just dividing the distribution by its standard deviation, right? So we did the same thing and we made it as a normal distribution with mean 0 and variance 1 z distribution, and we use the z test to check what is the value for c or alpha. Based on that, we will check what will be conclusion for the test. Let's say for alpha, for some fixed alpha, we got to know that our value of c is let's say something c naught, and the t x bar minus y bar is actually less than c. Then what will you do? If t is less than c naught, then you will say that what? Accept h naught, right? Is it so? You will accept or reject? If I got, you will accept h naught, right? Okay. Is there any doubt for this particular test? So this was two sample z test. we had two samples, but we were using z-test there, right? Is there any doubt for this particular test? Yes, anyone? Yeah.
Using these two tests, using our hypothesis, we converted it to one normal, no?
Yes.
And then we computed it with C, and then concluded that it is to be rejected or to be accepted.
Accepted. Yeah. Okay. So in a hypothesis testing, it has some steps, but at each and every steps, we have to take some decisions, right? What should be our samples? Like, for example, maximum of the times, this sample distribution is given to us. Just check whether they are independent or not. Now, the next point is check what should be your null hypothesis and what should be your alternative hypothesis. Once it's done, now check what should be your test statistics. Now, once you choose your test statistics, T, now decide whether it should be a greater than C, less than C, or depending on the alternative. Then select which test you have to use there. Okay. Once it's done, you will calculate the value of C and then you are through. Okay. So just be careful while using this test. Okay. So now we will check two sample F test. So any guess what might be the difference here? The above was two sample Z test. Yeah. What?
I think maybe the variance will take, in the previous case, we took the mean, right?
Yes, yes, same. So actually, whenever it comes to, whenever you see this Z test kind of thing, you can have one intuition that it might be about the mean. Okay. And always variance is kind of complicated thing. Okay. So let's say xi's and yi's are some IID normal distributions where xi's are following the normal distribution with mean mean nu 1, variance sigma 1 square, and yi is with another mean and variances. Okay. And the null hypothesis is about whether their variances or let's say standard deviation, okay, whether they are equal or not, or might be greater or less or whatever it is. Okay. Let's say they are not equal. So in that case, what should be your test statistics T now? Can we have a difference there? If we take the difference, then the things will be x bar minus y bar, and its variance will be somewhat like sigma 1 square by n1 square, right? This will be a variance in that case. So that will be tricky to check whether the variances are equal or not because there is a addition sign, right? So for that, do you remember this chi-square test? We have taken the ratio, right? So here also we will take the ratio. Let's say your test statistics is the ratio of sample variance for x bar and for y bar, okay? Or just let's say it's x or y instead of x bar and y bar because we have n1 random variables here and n2 variables here. Fine. So what will be your distribution for this sx and sy? So just don't just hold on it because we are saying that they are equal. So once they are equal, so if I divide it by sigma 1 and sigma 2, then it will be a F distribution, right? So what will be the test there? The same thing as we used to do, reject H naught, let's say whenever it is greater than, okay. So there is one thing that has to be keep in mind. Whenever we are going to have this kind of things, just take it as a modulus value, okay? Modulus T is greater than C. Now, what will be the significance level? Alpha will be a probability that of, again, a type 1 error, reject H naught, given that it is true. Now, here, what does it mean by H naught is true? H null hypothesis is true means, what does it imply in this particular case if null hypothesis is true?
If it is greater than 1.
Yeah, what? Sigma 1 is equal to sigma 2. What?
If
What
T
is
greater
greater
than
than
1.
1? Sorry. What's greater than 1?
If this ratio is greater than 1.
Okay, why it should be greater than 1?
Because we are checking for equality.
Null hypothesis is true. Only we are checking whether it's true or not. Ultimately, it will give you the same, whatever you say. That is correct ultimately. But if the question is only this, null hypothesis is true, that means your sigma 1 and sigma 2 are going to be same. If they are same, then what will happen? Then this ratio, Sx square by sigma 1 square upon Sy square by sigma 2 square will follow a F distribution with some, what we say, degree of freedom n-1 for Xi's and n2-1 for Yi's. So if they are equal, that means this can be cancelled out, right? So whatever our test statistic T that was equal to Sx square by Sy square will follow F distribution, right? Are you getting me? If they are equal, then they can get cancelled. And this is ultimately a F distribution. So once, yeah.
But in our steps, we started with Sx square upon Xy square.
Yes, we started with that. So if Sx square upon Sy square is there, then we may assume that this is a chi-square distribution, right? Are you speaking that only or something else?
Yes, ma'am, that only.
Yeah, chi-square.
We have taken H naught.
H naught.
Considering sigma 1 is equal to sigma 2.
We are not considering. When we will find out the significance level, at that time H naught will be true. Once H naught is true, then this will instead of being chi-square, this will become a F distribution, right? Because there is something hidden behind that, isn't it?
But my doubt is on what thought we started that Sx square by Sy square.
This one.
Above step.
Okay, above step. That is variance, based on the variance. Whenever we will check the hypothesis for the variances, we always take the ratio of variances. Now, obviously, we are checking for the population variance. We do not know what is sigma 1 and sigma 2 value, right?
Oh,
but
for
we
sigma
know
1
one
and sigma
thing.
2, we have taken Sx square.
Yeah, what is Sx square? It is, I should write it as Sx bar square. We have sample for X, right? So I can have variance for sample mean. I can have variance for sample mean of Xi and sample mean of Yi also, right? So I took the variance from there. What are the variances, sample variances for xi's and yi's. Okay,
Yes, ma'am. Got it.
fine. Okay. So once it's going to follow a F distribution. So remember one thing, F distribution is not symmetric, right? I just told initially. F distribution always looks like this. Somewhere here 1 we have, and the distribution is like sorry. This kind of distribution we have for the F distribution. Somewhere here or here we have one. So here, instead of taking modulus t greater than c, we can have different, what we say, limits for left limit and right limit for t. That it might be, this is again a choice. You can decide on your own, or depending on the context, we will take whether we have to take it as a 1 plus, let's say, CRR means right-sided limit, okay? Then it will become what? One-sided test, right? One-tailed test. Is it fine? It will be a right-sided test, right? Because we are putting limit on the
Yes,
right.
ma'am.
1
Got
plus
it.
CR will be somewhere here. Why I am explaining it separately? Because this is not a normal distribution. So things will work different here. In normal distribution is symmetric about its mean value, right? But this is not. Or you can have this, or both the limits also you can have. So whenever, see, whenever there are two sample tests and we are looking for the sample, we are looking for the population variance, then it is obvious that F distribution will come into the picture. So if you want to take two-tailed test, then take this both the limits, okay? Instead of taking modulus t less than c. If you are in the one sample test, that is which we discussed before this, in that case you can have modulus t less than c because they are going to follow a normal distribution. They are symmetric about a central value, right? Central value generally mean. But whenever it's about F distribution, it's not symmetric. So be careful with it. You can have your limits greater than 1 plus CR and or less than 1 minus CL. Okay. So CR and CL, again a critical value. Based on that, you will decide whether to accept null hypothesis or reject a null hypothesis. So again, revising this thing. So what will be here? If xi's are normal, like IID samples which are normal distributed, yi's are also IID normal samples, and we are checking for the variance of the given both the sorry, differences between the variance, whether they are equal or not, variance for xi and variance for yi's. So we will take the ratio of what we say, sample variance for xi's and sample variance yi's, and decide our test that if it is greater than 1 plus CR, we will reject H0, otherwise we will accept. Or similarly, there might be a new test which says that we will reject H0 if T is less than 1 minus CL, okay? And or it may be, if you want to have a two-tailed test, then take both the conditions, okay? So then alpha will be probability that rejecting H0 given that H0 is true. So now H0 is true here, that means sigma 1 and sigma 2 are equal, and once we know that thing, we will say that okay, it's going to follow a F distribution. Once it's an F distribution, now you will say where to use this F distribution. So your alpha is probability that T is less than, I'm just taking this part, okay? T is greater than 1 plus CR, okay? But we have both the choices. So let's say T is, yeah.
I did not get this CL and CR.
CL and CR are nothing but the critical value. CR means critical value on the right side because one is fixed here. One is there. CR means if you are taking the right sided test, instead of saying C, I am just saying it as CR. Okay?
Okay, got it.
There's no difference. I can remove CR also. 1 plus C, let's say. Or you can say T greater than C. That is also fine. Given that H naught is true. Okay. So, how to do that then? So what is T? T is actually following what? T is equal to Sx square upon Sy square. And also it was given that sigma 1 and sigma 2 are equal. So I will say as sigma 1 is equal to sigma 2. Why it is? Because I am saying H naught is true. Okay. So H naught is true. That means sigma 1 is equal to sigma 2. That implies my T is nothing but sigma 1 square upon Sy square by sigma 2 square. Generally, we take that only. Instead of this, I should write here also that we are taking this one only. Okay. So it will be something. So what is my distribution for T? It's nothing but the normal distribution for what? It is normal distributed with mean. Yeah, what was mean for T? Sorry, it's not a normal distribution, it's a F distribution with degree of freedom n-1 and n2 minus 1. So using that, this alpha is nothing but 1 minus from this part, okay? And just, okay. So T is nothing but the F distribution with Mn minus 1 and F2 minus 1. So alpha was what? Alpha was probability that T is greater than 1 plus C such that H naught is true. So, or you can just say it as a C, that is also fine. I have just added 1 because we always know whenever we have this kind of stuffs that it's going to end up with the F distribution. So if T is greater than this one and we know that this T is following T will follow F distribution whenever H naught is given already. So for as a whole, this will follow a F distribution and we will have 1 minus F of n1 minus n2 minus 1. We can just calculate it. We can just calculate it, and based on that, we will have the value for C. And using that, we can check what will be the values for C. And once we know whether the C is greater than, let's say, we solved it and we got the value C as C naught. And also, as xi's are known to us and yi's are known to us, we can calculate T, which is nothing but Sx upon Sy, squares. And we will check whether this value is greater than C or less than C. Based on that, we will check whether we have to accept the hypothesis or reject the hypothesis. Okay. So, what test we have learned today? Just revise that once again. Z test, T test, right? they both are, first of all, they are one sample taste, right? One sample taste, and we are looking for the mean, like hypothesis for the mean. Now, if let's just make it as one sample taste we are doing, and we are making hypothesis for mean. In that case, if variance is known, then we will go for z-test, right? Then go for z-test. If it is not known or unknown, in that case, we'll go for t-test. Fine. But remember, we are checking for hypothesis. The hypothesis test is for mean. Now, if we check for the variance or sigma, in that case, what we'll do? If it is a one sample test and we are checking for the variance, we will go for the chi-square test, right? And what if we are going for the two sample test? In two sample test, there is again, if we are checking for the mean, then we will use z-test, right? And if we are checking for the, like, let's say null. Yeah. Let's say null is mu1 is equal to mu2, like kind of the difference, or sometimes it may be like this, that the difference between mean is equal to 2 or not, like that. Okay. Comparison between the mean. In that case, your h1 will be, let's say they are not, the difference is not equal to 2. That is also the same thing. Okay. In that case, we will use z-test. And if the two sample test is checking for the variances, whether they are equal or not, in that case, what we'll use? In that case, we will use f-test. Okay. So we will use f-test. Okay. So this was all about the hypothesis test we learned today. Okay. So I hope you guys got it, how to check which test has to be applied there. On Tuesday, we will have a solve with the session where we will solve some questions based on this test. So that will clear it. That will clear concepts more, I guess. So if there is any doubt regarding today's session, you can ask the questions for that. Is there any doubt that is, or any topic that is not understood clear to you? You can check. Yes, any doubt there? Okay, then you can unmute yourself. Okay.
Okay, ma'am. Thank you.
Okay, thank you.
Thank you, ma'am.
Thank you. Yeah.
Thank you, ma'am.
Thanks. Okay, then see you on Tuesday.